Thank you, Artem, and good morning, good afternoon, or good evening to everyone attending Hot Interconnects. I'm Dan Pitt. I chair the subcommittee for keynotes and panel discussion, and I am dressed up today. I don't normally go to work like this because I am celebrating that Deepak Bansal from Microsoft has accepted my invitation to give a keynote at Hot Interconnects. Uh, Deepak has had really an exceptionally influential career and has been a pleasure to work with. He's been at Microsoft for a couple of decades. He graduated from IIT Delhi and from MIT. And I met him when he was on the board of directors of the Open Networking Foundation for basically all of the 6 years I was there from its public launch. And he had two roles really in ONF, the Open Networking Foundation. He was on the board of directors representing Microsoft, which was a founding board member. He also chaired the Configuration and Management Committee. We had really three technical committees, and that was one of them, and this really important work. And in those early days of SDN and the open flow protocol, we were just infatuated with the technology, and we loved what it could do to change how switches and routers worked and how management worked. But it was Deepak who always pulled us back and said, let's look at a higher layer. We've got to have an entire network here operating in some reasonable way. We have to be able to manage it and run it and configure it. And that took us away from sort of the eyes right on top of the technology of how you get forwarding tables put into switches and routers, and made us think about the larger context of what we were trying to achieve here. And those inputs and constant reminders to Deepak were extremely valuable. And they became concrete through his work chairing the Configuration and Management Committee of ONF. He's now Corporate Vice President of Microsoft, in charge of Azure Network Engineering, and I could not be more happy to introduce Deepak Bansal from Microsoft. The floor is yours, Deepak.
Thank you, Dan, for those nice words. And yes, I remember very well those early days when we were trying to get SDN bootstrapped with the cloud transformation happening in the world. And I feel like we are in similar phase now with uh, one second. Sorry, I'm trying to share my slides while I'm trying to speak here. So
Okay, we can see the slides. Just go back to the beginning.
yeah.
I saw you preview these.
Yeah. Okay. Let's see. I can take them back. Okay. Yeah. So, like Dan said, I remember more than a decade ago when we were trying to bootstrap the cloud networks, and that was a very fascinating phase in my career. And now is even more fascinating as we are trying to bootstrap AI infrastructure for the world. And I'm super excited to be here today and to share with all of you what we are doing in evolving the interconnect fabric and SDN in the cloud to meet the needs of the AI workloads. So when we look at applications, AI has been a game changer for more and more applications. It's disrupting every industry. It's disrupting all kinds of applications, from CAD, chemistry, molecular design, oil and gas, you name it. All industries and all applications are being made intelligent by infusing AI into them, right? It's a very fundamental shift, and the applications in just a couple of years from now would look very, very different and much more intelligent than we know of them today. But when we look at AI applications, right, they are part of a larger cloud ecosystem. These AI applications are hosted on a cloud infrastructure and they are made available to users through a network perimeter backed by various network functions. And these applications on the back end are accessing AI models and data storage to give an intelligent experience to the customers to be able to do the kind of workloads that we are becoming more and more accustomed for AI applications to do in this modern AI driven world. as cloud providers for these AI workloads, we must provide several things, right? We must provide private, secure, and reliable infrastructure to connect users to these AI applications. We must provide a very flexible infrastructure for these AI applications that matches the needs, the scale, the functionality that these AI applications are demanding. And we must scale our infrastructure very rapidly because AI applications are growing very, very fast. Chat GPT, Cursor, Klein, you name it, these applications are going through a hockey shaped adoption that we have never experienced before. And hence, the AI infrastructure that we are using to host these applications must rapidly scale at a breakneck pace to meet the requirements for these AI applications. So when we look at what these AI applications demand from the infrastructure, from an AI infrastructure in the cloud, they demand very high bandwidth, much, much higher bandwidth than we have ever seen before, right? And I'll share in next few slides the kind of bandwidth numbers that we are seeing that we didn't even imagine anyone would need just a couple years ago, right? In fact, I remember early days when video started becoming big with TikTok and YouTube. I was like, okay, voice is nothing, right? In terms of bandwidth for the infrastructure, and it's all video, and that was like a huge shift. We are going through a similar shift whereby video is nothing. It is the AI workloads demand on bandwidth that is outshadowing anything else that we have seen till now. And the networks these AI applications demand have to be super reliable, much higher reliability than, again, anything we have seen before. The latency that AI applications are demanding is very low latency because, again, end users are interacting with these AI applications in real time, and they require a lot of data to be moved around and to be able to respond to those user requests in real time. Another area that's super critical for AI applications is security, right? We do not want customer data to be accidentally exposed via models to where it should not be exposed to, right? Hence, AI applications demand that the infrastructure provides amazing capabilities to safeguard data and identity and make sure that data does not get inadvertently exfiltrated by the AI application. So let's look at some of the innovations that we are driving here at Microsoft to meet the needs of these AI applications. One such innovation I'm super, super excited about is this technology called hollow core fiber. And it's amazing technology. You know what it is the fiber that we have known and used and deployed for many decades now, right? It is made of glass, and that's how I learned physics of fiber. That's what fibers were always about. So when someone told me that speed of light can be increased, I laughed at them. I'm like, no, that's the fundamental law of physics. Except it turns out it matters a lot what medium the light flows through. When it is flowing through glass, it is slower than when it flows through air. And that's the fundamental thinking about hollow core fiber. The fiber itself has a hollow core. So the light actually travels through air slash vacuum. And by making the light travel through air slash vacuum, we are able to achieve 47% improvement in speed of transmission of data. And that's just so valuable when the demands for latency are to drive it down, and hollow core fiber is helping us achieve that. It also helps us in improved security because when you cut the fiber, you can no longer tap into the signals and tap into the data that is flowing through the fiber. Here is a short video of showing the lab where Microsoft is actually manufacturing these hollow core fibers, and we are deploying them across our regional networks, across even within our data centers now to meet the needs of these AI applications. So now let's look at the network inside the data center, right? So it used to be that we had compute clusters and we had storage clusters. That's the anatomy of a cloud data center that we've built over the last decade or so, right? But what happened with AI? There is a new beast in the town, and that's the GPUs. And now there is a GPU cluster that's standing side by side with compute and storage clusters. And what's going on is massive amounts of traffic is flowing east to west in across these clusters in the data center. While we used to have a lot of traffic flowing east to west between compute and storage, but now with GPUs are very hungry in terms of consuming data from storage clusters, feeding data from to storage clusters, and then compute talking to GPU, getting users' queries, handing over to the GPU cluster, which is accessing the storage cluster. Hence, a lot of traffic, petabytes of traffic is flowing within the data center backbone east to west. And we are actively looking at leveraging hollow core fiber even within the data center to improve the performance of the data center network itself. Next, let's go deeper at what we call the backend network. So the AI data center actually has three different networks, right? There is the scale up network, which is connecting multiple GPUs, typically within a single server or at a rack level. And then there is another network which is connecting multiple racks to each other, and that's the scale out network. And these two constitute what we call the backend network, right? And the reason we call them the backend network is because these two are the networks over which the GPUs communicate with each other, right? And then there is a whole another front end network, which is how GPUs talk to compute and to storage. And I'm going to talk a lot about front-end network later in the presentation, but let me focus on the back-end network first, both the scale-up and the scale-out part of the back-end network. So what's unique about AI workloads? And AI workloads fall into two broad categories, right? There are the training workloads, and then there are the inferencing workloads. Training workload is where the AI model gets trained on large amounts of data, and that typically takes a long period of time, in many cases, weeks and months. And that workload is highly synchronized. The way it works is all the GPUs do processing for a given stage in the pipeline of training. And then once they have processed all the data, they all communicate the outcome of the data to each other for the next epoch in the training itself. So what that translates into is that there are these bursts of data that flows through the backend network, and then there is a period of quietness on the backend network. But the period of quietness is marked by heavy GPU processing, except the caveat being the GPUs will start processing when everyone has received the data, because all the epochs are aligned in timeline. So you cannot actually start the next epoch till all the GPUs have finished the previous epoch. So that drives these large synchronous bursts of data, which puts a huge demand on the performance of the network, meaning the network has to be super reliable. The slowest communication is what governs the completion time of the workload, because every GPU has to wait for every other GPU to receive the data that is needed in time for the next epoch to run. And typically the way these AI training workloads work is that they snapshot the previous epoch outcome. And if there is any failed job, they may revert back to the previous snapshot and start the computation job all over again. So the retries of failed jobs is very, very costly. And as a result, you need to be very efficient in traffic management, in monitoring the network, and ensuring that it is error free, and any instability in the network are quickly rooted out of the network. And as a result, a lot of innovation we are driving to drive lossless traffic with low latency. Another unique challenge that the AI workloads put on the backend network is these large fat flows, which make the traffic not very friendly to ECMP, meaning there may be a large fat flow which is going over one part of the network, and there is no uh, and it may overload one part of the network, whereas there's plenty of bandwidth available in the remaining network as part of the class or fat tree topology. So we need mechanisms to engineer traffic such that we cannot just rely on ECMP, but we have to do more to distribute traffic for these fat flows across multiple paths. So we have done a lot of work in innovating on the backend network, and these technologies have been made available as part of Sonic for AI networking. Sonic is our open source effort to drive software for the network devices in the data center. You can think of it as it's really the Linux of networking. And all the innovations that we are doing in backend in improvements to the backend networking for AI, we are driving those through Sonic. One such innovation is segment routing over IPv6. What this enables is better control of the network path. So you can avoid unhealthy network paths, and you can manage load in the network more efficiently by leveraging this technology. Another technology that we are working on, and that is very fundamental to AI workloads, is packet spray. As I talked about, AI workloads tend to have fat flows where ECMP is not very effective because a single flow may overload a part of the network. So with packet spray, packets from a single flow get distributed across a large number of links in the class network. And as a result, the network load is more uniformly distributed, thereby enabling us to avoid losses and utilizing the bandwidth in the network more efficiently. Another key capability that we've been working on is what we call packet trimming. This is the technology that helps us detect packet losses much faster in the network than traditional mechanisms where you had to wait for certain timeout and then ask for packets to be retransmitted. But by packet trimming, we are able to take packet header and send it through another path in the network. Thereby, the receiver is able to quickly detect that the packet has been lost and can more effectively drive retransmission of the packet and loss recovery. Another very fundamental need for these AI networks is high frequency telemetry, right? And this is needed because, first of all, these AI networks are very large. And I'll show a slide just in next few minutes that show the scale of the AI networks. But at that scale, especially when the slowest guy in the network is the one who is determinant of the performance of the network, you need to be able to quickly detect failures, diagnose failures, and auto mitigate those failures. So let me first show you how big these AI networks have become. Some AI clusters now have more than 100,000 GPUs, and these GPUs create all sorts of problems, from cooling that we are working on addressing with OCP chassis and rack design, from the build out challenges itself, right? If some engineer or a network operator wired up one router port incorrectly, that will be highly costly when the AI training workload is running and using that network. So achieving defect-free build-out is very, very critical, and we have been investing heavily in a high level of automation so that we can deliver defect-free builds for our production data centers. And then the Ethernet slash InfiniBand technology itself that gets used for the backend network can encounter errors, right? These are hardware errors that can happen anytime in the network. So we have been investing a lot in defect detection and quick diagnosis via streaming telemetry. And this is new work that we've done where we take the telemetry data from the routers and switches in the AI network, send it over to distributed collectors, and then these distributed collectors deliver them to the cloud, the information that is coming from various routers and switches in the AI network. And then we apply AI itself to detect failures in the network on an ongoing basis and to take automated corrective measures when defects are detected. That way, we are able to resolve issues in the AI network in real time without involving the human, unlike the cloud era when we would rely on human or manual intervention many times to mitigate failures or unhealthy devices in the network. But in the AI world, given the scale and the real timeliness requirement, this all has to be automated, and leveraging AI to automate monitoring and detection and diagnosis has turned out to be a game changer for us. I briefly alluded to the fact that training and inferencing are two different kinds of AI workload, model-related workload. A training workload typically rely on a scale-out architecture where there are 100K GPUs, so lots and lots of GPUs that will be needed to train the model. And those GPUs may be shared with inferencing workload, where typically it is scale up or scale in AI technology, where few GPUs work together to answer a given user query to perform the inference job that is given to the model. So these AI workloads have been driving a huge increase in demand in terms of the infrastructure and more specifically the GPU itself. And many times it's not possible, or I would say in today's world, most times it's not possible to deliver all that GPU capacity that may be needed by our customers in a single location, single data centers. And customers themselves have AI workloads that are getting access from all over the world, and they want to bring AI technology to their application that is deployed worldwide. And hence, regional or global presence is critical for customers' AI workloads. Fortunately, Microsoft, as part of building the world's largest cloud environment, has a very extensive global presence. We have 60 plus regions, 275,000 miles of fiber that we have deployed connecting all our cloud regions. We built one of the largest WAN in the world as part of building the cloud platform, but AI has supercharged that WAN, and we have been adding capacity to our WAN like crazy. And at this point, we have 2+ petabytes of WAN capacity growing rapidly, tons of tiering capacity, as well as we peer with all the leading ISPs across the world. So you truly need this global scale of WAN for AI workloads because your users are distributed all over the world. Your application is distributed all over the world and accessing data and model that may be located in different parts of the world. And we are investing extensively in schedulers that are able to take customers' workload demands and allocate GPU capacity and storage capacity based on those global demands in sort of a global optimization problem. So now so what I've talked so far is more about the backend network, right? How do GPUs connect to each other, and how do applications connect to GPUs? Now let me shift gear and talk about how the application connect to the GPUs, right? And what is needed by an application, an AI-enabled application, right? It of course needs the model which is running on the GPUs, but then those models need to talk to storage, right? So it needs storage that itself is in the cloud, and then it needs compute, which is the front end, which is taking customer queries and requests and then invoking the model as well as the rest of the application workflow to give an intelligent answer to the customers. So as part of this application architecture, the compute and the GPUs need secure access to Azure storage. Because what we don't want is the storage to be somehow exposed outside the customer's boundary, because exposing data outside the customer's boundary makes it easy for that data to somehow be leaked or made available to where it should not be made available. And you all have heard about prompt injection threats and gaps, and so securing network access to storage is one of the key capabilities that help us provide security for AI workloads. Next, these GPUs, which may be located in a different region, may be located in a different partner data center, because again, a single provider may not have enough GPU, so customer may be leveraging GPUs from another provider. So these GPUs need to talk to storage securely. And what we have done here is we have built this technology that we call AI appliance. And it's a super cool technology. What it is built on is another key infrastructure component that has started showing up in data centers recently, and that is called DPUs, right? Data processing units. So AI appliance is built on top of DPUs, and it takes traffic coming from the GPUs and makes them access storage securely and privately in the customer's network, so that the traffic from GPU to storage doesn't have to leave the customer's network. And the reason we needed DPUs for this AI appliance is because traditionally we have built network appliances in the cloud on commodity gear, on commodity servers, and that has worked well to meet the scale needs of traditional cloud applications. But these AI applications, they are not happy with 100 Gbps of throughput. They want terabits of throughput. In fact, 12.8 terabits plus is something that we are able to achieve today, going from GPU to storage via DPU-based AI appliance. And that has really unlocked a lot of performance for AI workloads, and lower training and inference times, and improved efficiency in a dramatic fashion. The AI appliance is the beginning, in the sense that it is the kind of technology that is needed to improve the performance of network services that are needed to deliver AI applications. And one of the things that we are doing in this space is what we call smart switch. And what essentially a smart switch is, it embeds DPUs inside a switch itself. And we have an effort called DASH, disaggregated SDN, and it's part of the Sonic umbrella itself. It's a set of standardized APIs to program the DPUs. So by embedding DPUs in the switches itself, we are able to provide accelerated network services that I talked about in the previous slide for all kinds of AI workloads, without being limited by having to deliver those network services on commodity servers. Okay, let me shift gears now and let me talk about application networking for AI. So far, I have talked about the physical infrastructure. That's the infrastructure, the routers, the switches that sits inside our data centers, that make up the WAN, that connects our data centers, as well as edge technologies that connect partner data centers to Microsoft's cloud. But on top of this physical infrastructure, applications need an application networking stack for their workloads to communicate with each other. And typically AI applications are built on container technologies, right? Leveraging Kubernetes that they're using to manage the AI workload itself. So what we have done in the application networking space to deliver the cutting edge network stack for AI applications is we have built this amazing high performance network stack called Azure Managed CNI. And CNI stands for Container Networking Interface. This is the interface that multiple providers can plug into underneath Kubernetes to provide networking for Kubernetes workloads. And in Azure, we have built one such plugin, which we called Azure Managed CNI. And what this Azure Managed CNI, it is based on eBPF Cilium technology, which is well established in the industry as the leading network data plane for containerized workload. So we are leveraging it and we have enhanced it with a lot of optimizations that are tuned for AI workloads for high performance, low latency, and great diagnosability. We have added security features to it, advanced layer 3, layer 7 policies and encryption. We have added observability capabilities to it, and I'll talk about these in just a second. And last but not the least, the AI workloads typically get deployed over multiple Kubernetes clusters because the AI workloads are massive, right? Let's say you have a retail website that is AI enabled, right? So it's deployed on millions of cores, and when you're deployed on millions of cores, that gets deployed across multiple Kubernetes clusters, and hence operating these multiple thousands of Kubernetes clusters in a unified fashion such that networking for them is simple and easy to manage is critical. And hence, as part of Azure Managed CNI, we're investing significantly in multi-cluster capability to connect these clusters in a seamless fashion to each other. Okay, so this slide shows more details of what I talked about in the previous slide, right? On the left, I'm showing the data plane for the app networking built on top of Azure CNI. I mentioned already it is built using Cilium. It is most performant scalable data plane for AI workloads. And what we've done is we've extended Cilium to work on top of hardware offload technologies that we've built in the cloud over the years, right? You may have heard of SmartNIC technology that we built for the cloud workloads, but now we are able to leverage that SmartNIC technology in Azure Managed Cilium, such that the Cilium stack running on Azure delivers line rate performance without being bottlenecked by the host or the guest stack, and hence AI workloads can get the low latency and high performance that they demand. I talked about AI workloads being massive, deployed over millions of cores. So we have built capabilities in the IP address management space and in the network routing and connectivity space, such that you can have over 1 million IP addresses that are used for your AI workload assigned to the containers or the pods that you're running, that is hosting your AI workload. I briefly mentioned layer 4 to layer 7 policies that we have built as part of Azure Managed Cilium. These policies are implemented in a scalable way such that they do not get bottlenecked by the service layer. We support filtering on FQDNs, we support encryption. And then we have done a lot of work in improving observability and AI insights for this app networking stack. We launched this project called Retina in the open source, I think about a year ago now. And Retina has absolutely been a game changer in terms of being able to quickly diagnose network connectivity and performance issues. What it does is it supports ability to do distributed packet capture across large number of pods. It enables you to look at fine-grained metrics like DNS loss rate, packet counts at a given port level, and it's integrated into Prometheus and Grafana and Hubble. So you can see all the network statistics and diagnostic data for your entire cluster and multiple clusters in Prometheus, Grafana, and Hubble dashboards that customers have become accustomed to as part of their cloud infrastructure. And now those become even more important because AI workloads are even bigger and require observability and diagnostics at an even larger scale and with greater simplicity. And with Retina, we are able to support that. And the amazing news about Retina is it works across Linux and Windows. It works across Azure, on-prem, as well as other cloud providers. In fact, we have customers using it on GCP and AWS. So it's truly become this platform for observability, for network observability for AI workloads across the clouds, across all kinds of AI infrastructure. Another area in the application space, application networking space that we are looking at is what we call AI load balancing, right? Traditional load balancing has worked on the protocols of the past, I must say at this point, TCP and HTTP. And I know I cringe when I say protocols of the past because, I've grown believing that TCP and HTTP will never go away. But I'm starting to change my thinking, right? MCP is becoming the protocol of the future. And hence, load balancing also has to evolve to support the needs of AI workloads, to support these new protocols, right? Caching has to be rethought in the AI world, right? It's no longer okay to cache just at the content level, but it has to be a semantic cache because there may be different prompts that semantically mean the same. So you need to cache and be able to return the response based on the semantic meaning of the prompt rather than the exact syntax or the exact prompt itself. Prompt injection attacks that I talked about, right? So the WAF capabilities that traditionally have been part of the front end for various applications that now needs to support prompt injection prevention. The load balancing itself has to take into account metrics that are no longer just CPU and memory because some prompts are more costly than other, or they may be more costly on one server compared to another server because the data locality on the other server or things like that. So essentially we are rethinking load balancing in the AI era, right? What does it mean to load balance AI workloads? Another area that is super critical here that I alluded to earlier is regarding security, right? We have seen a lot of concerns and valid concerns and breaches where AI has inadvertently exposed customers' data where it should not have been exposed, and investments are being made to make AI be more secure in itself. But in addition to that, we need to secure the data better because if we secure the data better, then even if there are gaps in the AI layer, the data itself cannot be exfiltrated because the model itself is running inside the customer security perimeter. The data is inside the customer's security perimeter, and the workload is inside the customer's security perimeter, and that avoids inadvertent exposure of the data that is super critical for our customers. So we have built technologies. Some of these technologies we built for the cloud that we are now adapting to AI workloads, and some of the technologies are new, which have applicability in the cloud workloads as well, but are even more critical in the AI era. One such capability is network security perimeter, and the simplest way to explain it is it is there to secure storage resources, databases, right? When we look at customers' deployment on a cloud, we find that their storage and SQL and databases are not properly protected because as part of bringing data to the cloud and making it accessible to their applications, those storage and past resources have been inadvertently overexposed. So, and part of the challenge with overexposure has been there are lots and lots of storage accounts and SQL databases, and securing all of them in a man has not been easily manageable. So what network security perimeter does is it enables you to put different kinds of PaaS resources and lots of PaaS resources into a single perimeter there, and then apply security policies on that perimeter, and as a result achieving consistent security posture across different kinds of resources and large number of PaaS resources. And hence it enables customers to manage the security of their data far more effectively than has been possible in the past, and that enables them to secure their AI workloads better. We already had a capability called Private Link that enabled customers to connect compute to their PaaS resources, to their storage resources in a secure fashion. What we are finding is while Private Link was a highly desirable capability for traditional, and traditional here means cloud workloads, for AI workloads, it's a must have, right? Our AI customers always connect to their PaaS resources, to their data over Private Link from compute, and they mostly, in almost all cases, never choose to expose their data to the internet. And that's a very fundamental shift that has happened as part of this AI transformation, because customers are so much more aware and so much more concerned about the security of their data, because while in the past customers may have relied on data not being discoverable, everyone knows that AI will find the data no matter where it exists. All it needs is a right prompt, and hence you can no longer rely on security by obscurity, and you have to up the game on security and making sure that the data is really really secure. Because otherwise AI makes it easier to be exposed, and hence we are finding a massive adoption and new capabilities being delivered to enhance the security of the data. Okay, so let me start wrapping up here and just give a brief summary of the various innovations that I've talked about. And I would say this is the beginning, right? This is what we know so far. There is so much more innovation that has to happen in this space, because the requirements are very demanding, and there is a lot of unique needs that the AI workloads are driving innovation around. So one area we talked about was extreme scaling, going from 800 gigs to 1.6 terabits to 12.8 terabits, and that performance as well as low latency is being delivered by innovations in the WAN around hollow core fiber, innovations inside the center networking via improvements in protocols and packet loss handling through Sonic and Dash technologies, improvement in transport protocols, as well as improvements in telemetry to be able to detect faults in the network and be able to automatically recover from those faults. And by the way, this streaming telemetry that I talked about is also being made available in the open source for other customers to benefit from. Right? We talked briefly about how we are leveraging DPUs to connect remote GPUs to storage and compute, and thereby delivering more than 12.8 terabits of connectivity from GPUs to storage and to compute in a secure fashion. That's what I mean by SDN policies here. And then we are enhancing the security of the AI workloads by protecting the storage and the PaaS resources via technologies like Private Link as well as network security perimeter that I touched upon. So we are on a mission to build the AI infrastructure for the world. Microsoft is making massive investments in this space, capital investments $100 billion and growing, and to really enable our customers to build the future of their business on AI. Very soon, there will not be any app, or if an app is not AI enabled, it will be called a legacy app, right? That's the future we are marching towards, and having cutting edge infrastructure is absolutely critical for that future to be realized. And we are on a mission to deliver on that future, and looking forward to working with all of you, with the industry, in achieving that mission. It's actually a super exciting area, time to be in the networking space, to be in the technology space. Like Dan alluded to earlier, right? Cloud was the first transformation that happened, at least during my lifetime. Or internet was probably, internet and mobile, I would say, were the other ones. But this transformation of the infrastructure for AI is happening now, and we're all part of it, and looking forward to seeing what the future brings for us in terms of the AI infrastructure. Uh, that was the end of my presentation, Dan. Um, Over to you.
Fantastic, Deepak. It's so much to absorb. For one thing, will you make your slides available for our attendees to download? That would be great.
Yes, yes.
Could I ask one favor? Could you remove the confidential markings on them,
Oh, okay. Yeah,
please?
my bad. That was a miss on my side. We'll remove
Don't want
those.
anyone to get into a conflict of interest. We have one question on the Slack channel, and I would invite anyone else with questions to go to Slack, look for Keynote 2, and submit their questions. Oh, there's now more. Whoa. Okay. So the first one that came in is this. Does the WAN provide enough bandwidth to use DPUs? Could you elaborate more on that? And he means for the AI appliance.
Yeah, so great question. As I alluded to earlier, we are making massive investments in scaling up our WAN bandwidth. And I wouldn't say that it's homogeneous across the world. There are parts of the world where our WAN is much higher bandwidth, and we have reached those 12.8 terabits per second, or higher WAN bandwidth, connecting, say, one region to another region, one remote region to a hero region. So yes, WAN provides that kind of bandwidth in specific areas where we have a concentration of GPUs, and CPUs and storage.
Could I just expand on that with a question I had? Could you be a little more specific about what constitutes a DPU, what it does, and how it's distinguished from all the other XPUs?
That's a great question, and unfortunately, I'm not the best person in terms of. I'll give my best shot, but I don't know who in the industry invented the term DPU. Maybe it is Pradeep over at Fungible. I'm not sure, but the idea is that it is more specialized processor than a general purpose CPU. So it has those acceleration engines which can accelerate packet processing or storage processing or encryption uh, technologies. And by relying on those accelerators, you're able to deliver much higher bandwidth at a much lower cost, compared to if you were to implement those functions on software on general purpose commodity servers without any acceleration. And it doesn't make sense for us to deploy those accelerators, those beefy accelerators on each and every one of our servers, because not every workload is network intensive, and hence DPUs deployed in the network as appliances, where we can perform network intensive operations, is the model that we have found works the best.
In other words, they're packet and stream processors as opposed to computing devices.
That's a great way to put it, Dan.
So
Yes.
do they represent an evolution of smart NICs?
I think so. I think they are an evolution of smart NICs. The difference, I would say, or the evolution here is they are not only being used to accelerate host and VM networking, they are now being used to accelerate network services. right? Like load balancers or DDoS protection. And you can argue that the hardware load balancers and DOS appliances that have existed in the world for many decades were DPUs. They were FPGAs at times,
Yeah.
but they were not commodity. They were very custom built for specific function. They were not open source in the sense that they were not easily accessible to any vendor or anyone. But now the DPU technology has become standardized with P4 programmability and other technologies, frankly, Dan, that I think ONF started. So it's a great evolution of what ONF was out to do. Um, uh, but now it's just far more accessible for us to deploy at scale in our data centers.
And these are available from multiple manufacturers and foundries.
That is exactly right.
Okay, let's go to the next question, which is a series of questions from Bob Lance. And Bob says DPU is a smart NIC, right? That's probably before I asked the same question. So Bob says, really interesting talk and insight into Azure. I have a bunch of questions which you're welcome to pick from or ignore. And I certainly invite you, Deepak, to respond at any length you want on the Slack channel when you have a chance. I know you're on vacation in Europe with your family and it's already approaching dinner time, and I really appreciate you taking the time out from your holiday for us today. So let's see. How much, I'm just going to pick through these seven. Let me start with an interesting one to me. It's the last one. Is there any need or use case for programmable switches like the former P4 Tofino? Seems like they could also be used for applications like high-speed load balancing, or is everything being pushed to DPUs at the edge?
Uh, Thanks for that question. I briefly alluded to smart switch, and that is really the way we see the evolution of Tofino-based switches, right? Rather than having Tofino in them, which was a programmable chip, but the programmability was limited. Instead, if we put DPUs in those switches, it enables far greater programmability and far more functionality to be realized via those DPUs on those switches, and that's what we're calling smart switches. So I think smart switch is an evolution of Tofino kind of switches, except they are now beefier, or they have greater amounts of network processing, packet processing, and advanced packet processing capabilities, such that they can be leveraged to deliver network services.
So in other words, you're really using them for network engineering and not just telemetry.
That is exactly right. Yes, not just telemetry, and telemetry is super critical, and there's very important role that they play. But we are leveraging them for all kinds of network services, or planning to
Okay,
leverage.
great. So this is interesting. How much AI slash ML training versus inference do you expect to see? Do you have visibility to customer workloads versus Microsoft's workloads? And how does the network adapt to different workloads?
That's awesome question, and the world is constantly changing. I think if I were to look at what exists today, probably training workload is more, but inferencing is growing rapidly. So I think it's just a matter of time when inferencing is going to surpass training. Uh, but that's one of the things that we are ourselves learning as we are building the infrastructure, and as our customers' requirements and the workloads they're bringing changes. Uh, but I do feel that the demand for AI by the workloads is so high that it's just a matter of time before inferencing takes over training.
So a lot of inferencing is going to happen at the edge where the data originates. What is Microsoft's intention of doing AI processing, especially inferencing at the edge as opposed to into the cloud data center?
I think it will be a combination of both. There'll be a lot of inferencing that will happen at the edge on your laptops, on your mobile devices, in your car and whatnot. And that's the the workload that is very real time, where AI is sort of mission critical, and like you said, the data is local. But then there's a lot of inferencing that is happening in the cloud. Think Chat GPT, right? Chat
Yeah.
GPT
Yeah.
is all in the cloud. It's not at the edge. And we know there are tons and tons of use cases for Chat GPT, or for advanced image processing, enhancing your videos and photographs, whatever you see Meta doing. A lot of that is happening in the cloud. So I think there is room for both, and massive growth opportunity for both.
So you mentioned four categories of AI workloads: training, inference, AI apps and edge AI, and data pipeline. How do you design an infrastructure to serve such different types of workloads?
I think it's not that they are all disparate workloads. They come together and work with each other to deliver the end customer experience, and that's the beauty of it. That it's not siloed workload, but it's all interconnected, with where the apps and customer expectations are moving towards. That does place a huge onus on us to optimize across all those workloads. And when I talk about optimization, it's not just to give you an example, right? Availability is actually a big one. If any of those layers were to go down, the entire application is down at some level, right? And that's unacceptable. So each of those layers have to have very, very high reliability, because the end-to-end reliability of the app is composed of all of them, right? That's just one example. So I think that the tussle we face is how much specialized infrastructure we build for specific layer in the stack, versus how homogeneous it can be, right? And I think CPU, disks, network, GPUs, and DPUs, right? Those are probably the key infrastructure pieces, right? The hardware in the data center that believe are fundamental in the AI data center of the future, and they get composed into delivering on any of these five pieces. Um, Till maybe a future when something new shows up that we can't imagine today, that is super customized for one specific need. But I think those are the key infrastructure pieces that we are relying on to deliver each of these various aspects of AI workload.
Okay, let me boy, there's more. So here's one. Containers are challenging for GPU workloads if CUDA or other libraries in the container are version locked to the kernel driver, which is outside the container. How do you deal with this issue? Is there any way to fix it?
That's a good question. Unfortunately, I'm not expert in CUDA and in the container technology on the compute side. I'm more focused on network and network infrastructure and network services. So I'll defer that question to someone who's more knowledgeable, and take a pass on that question, Dan.
Okay. So let's see. All right, just we'll do, well, okay, 2 minutes. Um, Here's one from Daniel Chen. How fast can the telemetry support for sampling nowadays, and what kind of information could be gathered through the telemetry? He's interested about the high-speed telemetry supported by Sonic.
So I think that the key thing that I talked about there is streaming telemetry, right? Rather than offline analysis, or or some sort of sample based and sort of frequent snapshot based, right? And what we see is because of the real time need of the telemetry, we have to stream the telemetry data and process it in real time versus taking regular snapshots and stuff like that.
Okay, thank you. Well, Deepak, thank you for a hugely stimulating and informative keynote. And I really like your sort of even offhand comments as you went, which indicates that you've grappled with these things. And then there are tough questions, and we haven't solved all the problems. But I like your structured approach to the whole issue of cloud networking and cloud operations for AI. It's definitely something that the future is going to be dominated by. And so we're very grateful for your taking the time away from your family and your holiday to spend it with us. I should tell everyone that the Slack channel will be open for some weeks. So Deepak, if you want to wait until you get back from your holiday to go into depth on some of these answers, everyone can check back at their leisure to do so. So thank you, Deepak. Return to your family and have a good evening for the rest of your time.
Thank you, everyone.